Okay, let us understand phase diagrams today. Before we go on, we want to look at the term phase. So what does phase mean in chemistry? Phase is the state of a substance at a given pressure and temperature, meaning it can be a solid, a liquid, or a gas. Later on, you'll be also learning about critical fluid. So when we say a substance is going through a phase change, it is going through a change where it is in a solid state and it's either going directly to a liquid. The solid can also directly get into gas form. Obviously, liquid can also turn into a solid. Gas can also, in some cases, turn straight into a solid. Also, we can have liquid phases going into gas state and the gas state transforming into liquid state. So there are some terms you'll have to know of the different changes in phases. So when you go from a solid to a liquid, we think about that as melting. And in chemistry, we also call it fusion. When a liquid is turning into a gas, we think of it as evaporation. And when we have a solid going into a gas state, directly to a gas state, we call it sublimation. Going backwards, we can have a gas turning into a solid. That's called deposition. If a gas is going into liquid state, that's called condensation. And a liquid going into solid, we call that freezing. So all these terms you should know and memorize. Okay, so now let's look at a simplified version of a phase diagram. Here on the y-axis, we'll put the pressure, and on the x-axis, we'll put temperature. So our pressure will be in atmosphere units, and our temperature will be in Celsius units. So for example, we know that water boils at 100 degrees Celsius. Okay, so at 100 degrees Celsius, we know that at a certain pressure, and we know that this is at actually 100 degrees Celsius at 1 atmosphere of external pressure. That's sea level on Earth. So here is 1 atmosphere. And we know that right here we're going to have water boiling or water evaporating at that point. We know that water melts at 0 degrees Celsius at 1 atmosphere. So water is going to melt 0 degrees at 1 atmosphere. Okay, so seeing that these are 2 time points, so now I will actually draw the phase diagram of water where these 2 time points actually intersect certain lines. So let's do this. Okay, so again, right at this point here, we have the boiling point of water, and at this point here we have the melting point of water. How about all those other lines on all those other positions on the line? Well, that means that different pressures will have different boiling points and melting points for water. For example, if we go to the top of Mount Everest, the external pressure is lower. So let's say it's over here. That is, let's say 0.8 atmospheres. Let's say that's at Mount Everest, the highest point on Earth. So on Mount Everest, if we go across here, we intersect this line here, which is corresponding to all the melting points or freezing points of water. We'll hit this point here, and then we go down, and we see it intersects this point on the graph. So let's say this is higher than 0 degrees, so let's call it 3 degrees. So then we know on Mount Everest, water will actually melt at 3 degrees instead of 0 degrees at 0.8 atmospheres of external pressure. Likewise, if we go across and intersect now this line, coordinating to 0.8 atmospheres, and then we go down, we see that at this point here, which is less than 100 degrees Celsius, water will actually evaporate on Mount Everest at temperatures lower than 100 degrees Celsius. Let's just say around 80 degrees Celsius, water will actually start evaporating on Mount Everest. Okay, so I redrew the diagram to show you now labeled the regions of the phase diagrams for water: solid, liquid, and then gas regions. So from the last explanation I gave, you know that then this line then, this portion of this line coordinates to liquid going to gas state, or if you go the other way, so this liquid going to gas state, but if you go the other way, this is gas going to liquid state. Either way, this line then is about the transformation from liquid to gas state transformations. Obviously, liquid to gas, we call that, like I said, we call it evaporation. And gas to liquid, we call that condensation. So depending on the temperature, you can figure out the evaporation and condensation points of water. On this line then, the solid to liquid is all the freezing and melting points of water. Given a specific pressure, it will give you the temperature that this phase is occurring. So this is going from liquid, melting, and this is going to freezing. Again, the same temperature. So what happens down here from between the solid and gas state? Between the solid and gas state, from solid to gas, that is sublimation. From gas to solid, it is deposition. So going from here to here, this point here, you're going sublimation, and at the same pressure, you're also going to deposition. So let's take this point on this graph right here, for example. So water will be going through a sublimation and a deposition at 0 degrees at a very reduced pressure, obviously very much less than 1 atmosphere. So at this point, you have an equilibrium between solid and gas state. As in here, any point on this line is an equilibrium between liquid and gas state. And on this line, it's an equilibrium between solid and liquid states on that line. So here is a better representation of the phase diagram of water. Again, the labels are the same as before. As you can see, this line pertains to the condensation and evaporation points of water given a temperature and pressure. This is the melting and freezing point intersection given a certain temperature and pressure. Here, we didn't talk about it last time, but here is your sublimation and deposition interface between solid and gas states at a given pressure and temperature. What we didn't talk about is this point right here called the triple point. And triple point obviously is an intersection between solid, liquid, and gas. That means solid is in equilibrium with gas, which is also in equilibrium with both other phases. So they are in complete equilibrium. They all exist at the same temperature and pressure. So for water, if you had conditions where you had 0.006 atmospheres, and at 0.01 degrees Celsius, you would actually get this kind of situation happening. Another thing we have to point out is critical point, as up here, which is up here. So what does critical point mean? Actually, it means that at a certain very high temperatures, as you can see at 374 degrees Celsius, and at basically at an atmosphere of 218 atmospheres, very high pressure conditions, the transformation of liquid to gas no longer exists. Meaning at this point you cannot tell the difference anymore whether you have liquid or gas. They will actually not coexist, but they'll actually turn into a different type of phase, which is called, sometimes we call it plasma, sometimes we call it critical fluid. So this is the fourth phase that happens. Obviously we do not observe that on Earth at sea level because of the high temperature and high pressure conditions. Basically, you can see critical fluid happening in neon signs, not for water, but for neon element, or in lightning. Actually, in lightning is actually critical fluid. So again, at this point at the critical point, you can no longer see if it is liquid or gas. It's a new state called critical fluid. One thing more to say about the phase diagram of water is that you'll notice that the line which pertains to the freezing and the melting point is a negative slope. This is very different for water than for all other types of compounds. Water actually, as you can see, when you increase the pressure of water, of a sample of water, keeping the temperature the same, if you increase it, going, let's say, from here going from here to here in a straight line going up this way, water becomes a liquid. So liquid water is more dense than ice. That is then you can see that by the negative slope. In most other elements, as you get into more higher pressures, the substance becomes more like a solid, but in water it becomes more like a liquid. So here you have different phase diagrams for different types of substances other than water. On the left you have a phase diagram for carbon dioxide, and on the right you have the phase diagram for carbon. So these are very interesting, and you can learn a lot about substances by looking at their phase diagrams. For example, if you look at the phase diagram of carbon dioxide on the left, you can see at 1 atmosphere, so at 1 atmosphere, carbon dioxide is going to be a gas because room temperature is around here, so it's in a gaseous state. But at 1 atmosphere, it does not ever go to a liquid state. It goes from state solid to gas, from very cold temperatures to 31 degrees. So at minus 78 degrees, you have sublimation occurring. It goes from solid, carbon dioxide straight to gas at minus 78 at 1 atmosphere. And you can only have liquid carbon dioxide at very high pressures up here, and obviously temperatures in this range over here. That's when you can get liquid carbon dioxide to happen. Now on the right hand side, when we look at the phase diagram of carbon, first of all, we know carbon as two different forms of solids. We know carbon, a solid form, can either take the form of graphite or can take the form of a diamond. So just looking at the phase diagrams for the solid portion of which is over here, the solid phase for diamond, you're going to form graphite or a diamond. At the higher pressure, obviously, will form diamonds. Lower pressure will form graphite. If for some reason you want to have liquefied carbon, if you want carbon as a liquid, you have to have very high temperatures and very high pressures. But that can't happen, obviously. So this line here, any point on this line, and you will actually start liquefying or melting diamond and melting graphite. So you will actually start having the formation of liquid carbon. And if you wanted to vaporize carbon, then if you want to go from carbon liquid to carbon gas, which is pertaining to now this line, obviously high temperatures but lower pressures will do that. And the last one, if you want to go from carbon solid in graphite and go straight to carbon gas, so you want to sublime graphite, it'll pertain to this line here. What you cannot do then, from looking at the phase diagrams, you cannot go from carbon solid as a diamond form straight to a gas form. That will not happen because there is no line intersecting between diamond and vapor. Okay, so let's look at the triple point for carbon dioxide. As you can see from the graph, here it is, that's your triple point. So as you can see, the triple point for carbon dioxide is a little bit over 1 atmosphere. And it's not to scale, but obviously it is about, it's between minus 78 degrees and 31 degrees Celsius between there. In that point, that is the temperature of the triple point of carbon dioxide. For the triple point for carbon, it has to be this point here. That's the triple point. Because again, the triple point is when all three phases coexist at the same time, solid, liquid, and gas, are in equilibrium with each other. Think of equilibrium as the rate of change going from one phase to the other. Is there a triple point when it comes to diamond? No, there is not, because it never, again, a triple point is between three different phases. Diamond's triple point is which does not have, because the diamond region does not intersect with the vapor. Only the graphite region intersects with the vapor.